Okay, then welcome again. Fourth lecture of the day. Operating principle of piezoelectric transducers. So now, or in the last lecture, we had a more general introduction to multifunctional materials and to some key parameters. And now we will have a deeper look into piezoelectric transducers. So we are here in the last lecture block of the day. I will first give the lecture, and then after the lecture we try to show you a small live experiment based on the first lab experiment tomorrow. But then you can also already get an impression and maybe connect directly the theory to the experiments. Yeah, so outline basically operating principle of piezoelectric transducers. The learning objectives of these lectures are that you know the operating principle of the piezoelectric transducer effect. You can or should describe the polarization process on the crystal domain and ceramic scale. And you can draw and describe the hysteresis and the typical butterfly curve, including characteristic points. We will introduce, or I will introduce these two curves in this lecture, and they are also part of the labs. And then at the end, you can also state advantages and disadvantages of piezoelectric ceramic materials compared to other materials. So the piezoelectric effect was discovered in 1880 by the brothers Pierre and Jacques Curie. And they observed that in certain crystals, a mechanical stress leads to an electric charge, which is the direct piezoelectric effect. And owing to the inverse piezoelectric effect, piezoelectric crystals elongate when an electric voltage is applied. So this is the effect we use when we use them as actuators. And this inverse effect was predicted and theoretically described in 1881, so 1 year later, by Gabriel Lippmann, and was also shortly thereafter confirmed experimentally by the Curie brothers. So piezoelectric ceramics are electromechanical transducers. There is one material which is most common or predominantly used, which is lead zirconate titanate. We will also focus on in this lecture. The problem is that they contain lead, which is will be banned in the future, I think. And there are also lead-free alternatives, but they most of the time have a lower performance than the lead-based piezoceramic materials. And examples of applications you might know are piezo lighters. If you have a lighter where you just click and then the flame lights up, this is a piezoceramic crystal inside where you hit a mechanical stress on and then the lighter goes on. Ultrasound transducers, accelerometers, and also injection nozzles in combustion engine and diesel engines are also made from piezoceramics. And they can have as a semi-finished material the form of fibers and also of thin films or plates. But we will also, I think tomorrow, have a look into the manufacturing processes in general to get you an impression how these materials are manufactured. So with that, we move over to the operating principle. And the main reason or the cause of the piezoelectric effect is the crystalline structure, which has an asymmetry. So the charge center and the geometric center do not coincide in this case. If you look at this lattice, you notice that this atom here in the middle is not is not in the middle. It's not in the geometric middle, and therefore you have let's say geometric and charge center not coincide, and then an external mechanic loading leads to a distortion of this lattice, and therefore also the charge center moves, and this leads to a displacement of charge. We will have a deeper look in the next slides, but here it is we try to visualize this. Here you have the piezoceramic in the middle. You have a force deforming this piezoceramic, and then you have a positive and a negative charge at the sides of the crystal. So as mentioned, we have the direct piezoelectric effect, where mechanical stress induces an electrical surface charge. This is the sensor principle. So if you deform the piezoceramic, you have an electric charge which you can measure, and then you can use it as a sensor. And you have the inverse piezoelectric effect, where an electric field leads to a mechanical deformation. So you apply, in this case, have electrodes on the piezoceramic, apply here a current, and then the piezoceramic would deform, and this is the basic principle we use for actuating. So the inverse effect is for actuating. And we assume that the volume remains nearly constant. I will not show this video, but we will provide the slides, I think, in the evening, and here's also the link to this video. I think it's about 10 minutes long, and it's a nice explanation to the piezoelectric effect. So if you want to learn more about it, then you may have a look also in this video. The crystal structure of this piezoceramic material is a perovskite structure. It's a mineral class of oxides and hydroxides, and the perovskite structure has 3 different atoms or elements, A, B, and oxide, and A could be magnesium, zinc, scandium, niob, and so on, and B is, in our case, lead, or most of the time lead, and you can also have crystals with a grain structure, so not being a single crystal, but there are materials which are single crystals, like this one, which is PMNPT, lead magnesium niobate, lead titanate. Let's have a look at the perovskite structure. You have a cubic lattice of the crystal has a cubic lattice. Here in the middle, you have the atom A, which is one of these materials or elements. Then you have around the oxide atoms, and here on the edges of this lattice, the B atoms, in this case the lead. And the crystal lattice or the lattice structure depends on different things, the temperature and also the composition of the ceramic. And I'd like to introduce this at the example of the lead zirconate, lead titanate, PZT material. Here in this phase diagram, we have the cubic lattice, which is above this line, which is Tc, the Curie temperature. And if we cool down the material, then it changes to a rhombohedral or a tetragonal lattice. And these two then have the piezoelectric effect. The cubic lattice does not have the piezoelectric effect. And this here between these two lattices depend on the composition of the material. So we have lead zirconate and lead titanate and mixture of both. So at this morphotrophic boundary, we have a composition of nearly 50% lead zirconate and 50% lead titanate. And at this boundary, also the electromechanical properties of the ceramic are the highest. So we want to have composition near this boundary. And then it depends if we are below this boundary or above. When we cool it down from the cubic lattice, we get the rhombohedral or the tetragonal lattice. So for the cubic lattice, if we are above the Curie temperature, we have no electric dipole, so no piezoelectric effect. Because in the cubic lattice, the center of the positive and negative charges coincide and with the center of symmetry. So there's no piezoelectric effect. And if we cool it down below the Curie temperature, we get the spontaneous polarization. As I mentioned on the last slide, the cubic lattice transforms if we are above the morphotrophic boundary. In this case, it transforms to the tetragonal crystal lattice. And here you can see that this atom in the middle moves up a bit and is not longer the center of symmetry of the crystal. And with that, we form an electric dipole with the corresponding polarization direction, so in the direction where the element moves. This can happen in 6 equivalent directions of ionic displacement. So it, if you look in this coordinate system, it cannot only, or the element in the middle cannot only move up, but it can also move down, come forward, back, left side. So you have 6 directions in total. This leads to so-called domains. So you have the crystal structure, which is divided in grains. And inside these grains, you have different domains. And each domain has the same polarization direction. So this is the this characterizes the domains. Domains are lattice regions of homogeneous orientation of the spontaneous polarization. We could also have crystals with homogeneous polarization orientation, single domain state. And otherwise, we have multi-domain regions which are separated by domain walls. So if we look at this simplified structure, then here we have the element in the middle moved up. So this is a domain. Here's another domain where the element moves to the left or has moved to the left, and between them there is a domain wall. And here's the same with a different kind of figure with arrows for the polarization direction. So here it's in this direction, here it is down, up, here down again, and between these domains we have again these domain walls, which could be 90-degree domain walls. So it's nearly 90 degrees between these polarization directions. And here we have 180-degree domain walls, so polarization in this direction, and on the other side of the domain wall, polarization in the other direction. And there are uniaxial ferroelectrics, which have only 2 stable polarization directions with 180-degree domain walls, so only like this. And we have multi-axial ferroelectrics, which has several, often 6, like I showed, stable polarization directions, like maybe more on the left-hand side. So if we look at the grain domain structure of this lead zirconate titanate ceramic, upon cooling, the ceramic consists of multiple single crystals with random crystallographic orientation. You can see the crystals here with the black borders in this microsection. So these larger areas are the grains. And within these grains, you have regions of identical polarizations, so-called Weiss domains. And these are the light and dark contrast lines in the grain. So you have these striped grains, and the light and dark colors would be the different domains. And the boundary between these Weiss domains below the Curie temperature, we only have the effect below the Curie temperature is called Bloch wall, and the change in polarization in the Bloch wall between these domains exhibits a helical structure. So if we would zoom in this Bloch wall, we have here domain 1 and here domain 2. Here goes the polarization up and here down, and over lengths of 50 to 100 nanometers, the polarization direction of the crystals change. So when we have this polarization forms an electric dipole, and the electric dipoles are randomly distributed after the sintering process. If we go back, here we have after the spontaneous polarization, we could have these 6 directions of polarization, and this leads to randomly distributed dipoles, and the polarity has no macroscopic effects because the dipole moment cancel each other out between the different regions of polarization. But we can align the polarization or the dipoles by a sufficiently large electric field. So we need up to 2 kilovolts per millimeter. And with this, we can polarize the whole crystal structure. So we have this dipole, and we apply electric field, and then all the dipoles rotate and have nearly the same orientation. And after this polarization, we can use the effect, let's say, on a macroscopic level. And if we then remove the field again, this macroscopic effect where the polarization stays to amount of 90% of the spontaneous polarization. So we have a remanent polarization. If we will have a look in the diagram afterwards, but the field is, let's say, strongly aligned with the field. And if we remove the field, it goes a bit back, and this is then the remanent polarization without the field applied. Since the piezoelectric ceramics have these electric dipoles, they can be altered by an external field. They belong to the ferroelectrics, a term I already used before. So we use the electric field, or we apply one time before we use or have the macroscopic piezoelectric effect in use. We have to have this polarization process to really use it. So what happens during polarization, or how can we visualize this on the grain and domain structure? Before our polarization, so we cool it down below Curie temperature, then we have the spontaneous polarization state. This is this one where we have the grains, and inside the grains are the domains with different dipole orientations and the Bloch walls between the different domains. Then we apply the electric field. So here are the electrodes on top and at the bottom, and this aligns the dipoles in the grains, and also or in the grains, and also some domains will vanish, because then we have the same dipole orientations at neighboring domains. And if we then remove the field again, we will it results in a polarization state, but it's not that oriented then during the polarization, so it goes a bit back, or some of the polarization is lost. And if we have the piezoelectric effect, meaning we have an electromechanical behavior. If we apply the electric field, the crystal is elongated compared to its state, or its spontaneous polarized state. And if we then remove the field again, it will deform a bit back, and we have a remanent elongation, which is still a bit elongated compared to the state before. And before polarization, the piezoelectric ceramics are electrically and mechanically isotropic, and after that we have an anisotropic material behavior. We also have another type of figure for this, just to visualize the process. So we have these circles with the arrows for the polarization orientation, which is randomly distributed after the spontaneous polarization. And then if we apply the field, we have a strong orientation in one direction. And if we remove the field again, then we lose a bit of this orientation again. Describing this polarization process with this circle diagrams could also be a nice question for the exam, I think. So we can also depolarize the piezoceramic. It could be depolarized due to a mechanical stress. Then the depolarized condition looks most of the time so that we have some domains oriented to one direction and one into the opposite direction, but they will cancel each other out, so we have no macroscopic polarization. If we have a thermically depolarized condition, then we have this random distribution again, and we could polarize it again when you apply an electric field again. So what do we have to do to depolarize it thermically? Do you have an idea? What bound? Sorry? Electric field. Reverse? No. When it's so if you this is the spontaneous polarized state, then you apply the electric field, and if you remove the electric field, it's still polarized, but not that strongly then under the electric field, but it goes not back to this depolarized state.
If you reverse the electric field also.
Reverse. Okay, sorry. So if you reverse the electric field, you would lose the polarization. That's right. Sorry, I missed it. This is one option. There's another option. If you think of a temperature, maybe you know it. So if you go again above the Curie temperature, then you have the cubic lattice again, and then you lose the orientation or the spontaneous polarization, and then you have to cool it down again and have the polarization to have the macroscopic effect again. So you can't use piezoceramics if the environmental conditions are above the Curie temperature of the material. So if we look in this characteristic curve, which is the hysteresis curve, we have here on the x-axis the electric field. We have the polarization here. It's capital P, pi. And we start here in the middle. So we have no electric field applied, and we also have no macroscopic polarization. This is point A. So polarization or dipole orientations statistically distributed. And then we apply the electric field up to this point. It's not marked here, but this would be the maximum electric field. Then we are at this state B, electric field applied. We have a very high orientation in one direction. And if we then remove the field again, so we go up to this point, electric field is 0, but then we have the remanent polarization, so the polarization like this, not that oriented like in state B, but still a large orientation which we can use macroscopically. If we then reverse the field like you proposed, then the polarization gets lesser and lesser, and if we meet this x-axis, then we have here the coercitive field strength. This is the field strength where the polarization is lost. There we have the point D, where we have the same amount of dipoles oriented in the one and in the other direction, and then they cancel each other out and we can't use the effect anymore. If we then apply more or increase the field strength, at least the amount of the field with the negative sign, we will get to point E, which is, let's say, the opposite to point B, but just in the other direction. And then we can remove the field again. We have the remanent polarization, but in the other direction. And then we can increase the field again. Here's again the coercitive field strength, where we depolarize it, and then we could go back up to point B. So this green line is only for initial polarization, if we after cooling down from Curie temperature, and if we have it in a depolarized state due to field, then we are at this point and at this point, and then we follow just the black lines. There's another characteristic diagram. It's called butterfly curve, because it looks similar to a butterfly, which has again the x-axis with the electric field, but now on the y-axis we have the elongation epsilon and not the polarization anymore. And we can go through it, walk through it like in the other diagram. We start again with point A, so we have the same circle diagrams. So both diagrams are also nice exam questions with these characteristic points marked, and also the circle diagrams. And we have this initial polarization, green line again. So we go up here at a field and come up to point B, where we have the maximum polarization, or the maximum elongation also of the piezo ceramic at the maximum field, point B. And then if we remove the field again, we go down here up to this point C. We have it now, the piezo ceramic polarized, but no field applied. And by definition, or we could define this as zero strain, but we could also shift the butterfly hysteresis up so that this is defined as zero strain. It's a matter of definition. And if we then reverse the field again, we have the coercitive field strength again, where we lose our polarization, point D again. Then we increase the amount of the field, again going up to point E, which is the opposite of point B. So high polarization, but in the other direction. Then remove the field again. We're coming back to the middle here, point F, which is the same like point C, but with the other polarization direction. And then after this initial polarization, if we use the piezoceramic, we could, for example, use it between the point B and the point C. So we could use it going up with the blue line and then going down with the red line and going up with the blue line again. So this is the usable, or could be the usable amount of the piezoelectric material. So the butterfly curve again, E is the electric field strength, U is not included, EC is the coercive or coercive field strength. We have to look up the right translation in English. Emax is the maximum electric field at maximum operating value here. And yeah, the limitation of the maximum voltage is due to saturation and dielectric strength, and you would simply destroy the piezoelectric material when you go higher with the field. So this is again a part of the butterfly curve, but now with the operating range we can use. So we can technically use it between minus 1/3 of the coercive field strength and Emax, so between this point and this point. But to avoid electrical breakdown during operation, we usually limit it to 50% of Emax, so up to this point. So the blue, so going up with the green and then coming up with the blue line would be the hysteresis we use technically. Exceeding the EC would lead to a depolarization, as we saw with the circle diagrams, also in the hysteresis, and could also lead to mechanical destruction. We will have a look at tomorrow at a small signal operation where we could linearize the behavior to have a simple model or a simple description of the behavior. So what do you think is this area between these hysteresis curves? What could it stand for? Energy density? Yeah, electric field. So now here's U in the butterfly curve, but it could also be. So it's a measure of loss. So the larger the area in this hysteresis, the higher is the loss, for example, due to heating of the ceramic material. So if we look at these hysteresis now, so at these hysteresis with different electrical field time histories, then we can see that this hysteresis characterizes a behavior in which the strain does not depend solely on the independently variable input quantity, the electric field, but also on the previous state of the input quantity. This is the thing I mentioned in the lecture before with the unique transduction. If you look at a specific electrical field here, it depends on the history if you're going up and have this elongation, or if you're coming down from a higher field and have a higher elongation. So it depends on the history in the operation what strain corresponds to the electric field. And if we look at this example, so first the electric field is high, it's from 1 to 2, so we go here in this diagram from 1 up to 2 here. Then we remove the field again to 0, back at point 1, then we are here, then we apply a field again to point 3, but a lower field than before, then we come up to this point 3, remove the field again, then we are here, and then point 4 going up again, but even smaller field coming down again, and you can see that the area under the curve is also smaller if we apply smaller fields. And under large signal actuation, the loss in the hysteresis lies between 8 to 15%, so of the energy we put into the material due to the electric field. This is the same, well, a similar diagram, but with a different field time history, where we're not going back to 0 all the time, just at the end. So to look at the first loops, we're going from 1 to 2, and then going down to 0.3, so not to field 0 and also not to the elongation 0, and then increase the field again to 0.4. We are here and remove it again and so on, and in the end we are coming back here to the origin. And yeah, it's caused by the domain wall motion. Well, one cause is the domain wall motion, which generates heat in the ceramic, so it heats up and this generates loss. So we do not have an 100% transduction of the energies. These are some real measured butterfly curves and hysteresis to have some numbers. So here we have the electric field in kilovolts per millimeter and the displacement also in millimeter. And we are going up here up to 0.2, where we have 2.8 kilovolt per millimeter and an elongation of around 60 millimeters. And then if we remove the field again, we have still 40 millimeters. So this would be the remanent displacement. And also here the same, from the same experiment, electric field. It's not from the same experiment, it's in the operating of the actuator. So we're not going up to 2.8 kilovolts per millimeter, but just up to about 2 kilovolts per millimeter, and can use a displacement of 40 millimeters in this specific case. But we will also have a look in the live experiment, hopefully afterwards. So with this, I come to the summary of the lecture, and then we have a short break to switch the camera to the experimental setup, and then we will have a look at the experiment, and then we will close for today. So advantages and disadvantages of piezoelectric ceramics, like mentioned in the learning goals, we have large forces and high stiffness. We have high electromechanical efficiency, very short response times in microseconds, so we can also use it for vibration control or dynamic tasks. We have a rather small energy consumption in static operation. Different assignments of field and strain directions are possible, and the materials are highly available, so different ceramic materials, for example, the lead zirconate, lead titanate. And the disadvantages are that the material parameters are temperature and aging dependent. We can lose the piezoelectric effect due to high temperatures if we are above the Curie temperature, due to large field strength or to a mechanical shock. We have a pronounced hysteresis, so no unique transduction, and we have significant heating of the ceramics if we have it in dynamic operation, and we need a high voltage power supply for the capacitive load. As we saw here, we are going up to really high voltage numbers, so you need high voltage amplifier like this one we use in the experiment. And with this, I come to the overall summary for this lecture. So the operating principle we can state is the non-centrosymmetric crystal. And with this, the mechanical stress induces a surface charge. So this is the direct effect, or an electric field induces a strain at approximately constant volume. This is the inverse effect. We need the polarization process after we have cooled down below Curie temperature. So the ionic displacement in a unit cell, domain wall motion, and domain reorientation within the grains the global alignment of domains during the polarization process leads to the remanent macroscopic polarization, which we then can use macroscopically. And we have these two typical curves, the hysteresis and the butterfly curve. So the ferroelectric capital P, so polarization over E loop with the remanent polarization and the coercitive field strength. And we have the elongation over the electric field, so the strain field butterfly curve. There we have the local minima at the coercitive field strength and the maximum at the maximum field strength. And from the slide before, advantages and disadvantages: high forces, high stiffness. Piezoceramics have Young's modulus up to 60 gigapascals, so we can really use it as a structural material. We have high dynamics and resolution. We only need low static power, but we have temperature and aging dependency, could depolarize it due to different effects, and we have a pronounced hysteresis, and we need a high voltage drive. So with this, I'm at the end for this lecture, and I'm open for questions. Yeah.
Electric susceptibility, anyhow it is high for a ferroelectric, but is there any bearing in this, coercivity and retentivity are pronounced in this? What about electric susceptibility?
I think if I get your question right, then you can dope this piezoelectric materials with different elements, and this leads to soft or hard piezoelectric materials. So the hysteresis curve would shift or increase its slope depending on the doping, because then the domain wall motion is easier or harder, so to say. Yeah. Okay. Yeah. Mm-hmm. You mean here? Next. So other direction, so this one? Yes, this. Yeah. 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 So I jump back to this slide. So we say that we need electric field higher than 2 kilovolts per millimeter to get the initial polarization, and then we try not to go up to this high value, so stay below 2 kilovolts per millimeter to not change the polarization of the piezoceramic material. So this is the polarization or repolarization, and we start with no displacement and no electric field. Then we apply the electric field above 2 kilovolts per millimeter and remove it again. Then we have the piezoceramic polarized, and we have this remanent displacement. And from this point on, we use, let's say, this hysteresis, and there we won't go higher than 2 kilovolts to not change the polarization. Does this answer? Okay. Further questions? Yep.
So like you have mentioned that we require at least 2 kilovolt per mm for the poly. So doesn't it depend upon the thickness of the material also?
Yeah, sure. If the electrodes are further away, then you need more power or more current, higher voltage.
If we decrease the thickness, so this criteria can be changed. Like it can be
No, no. This quantity is specific to the thickness. So you multiply it with the thickness of your material, and then you get the voltage you need. So if you have 0.5 millimeter thick material, you won't only need 1.4 kilovolts. And if you have material which is 2 millimeters in thickness, you would need 5.6 kilovolts. Yeah. Distance between the electrodes. Okay, then. Yeah. This one?
So just a silly question.
Yeah.
So okay, elongation positive. Is there any way we can control elongation direction also, like fixing one end like that?
I mean, elongation direction depends on direction of the electrodes, right? You have the field direction in between the electrodes, and we will come to that tomorrow. You can use the D33 effect, so the effect in which aligns with the direction of the field, and you could also use the effect perpendicular to the field. But so you could change the position of the electrodes. Yeah.
In all these cases, the change in area is very, very negligible. So
yeah.
ignoring.
Yeah. So this is what we assume, at least. Yeah. Okay. Then we take a short break, maybe 5 minutes.
We do not really need a break for the camera and everything.
Okay. Then
just continue.
Then we go ahead. So we.
Bitte einmal Kanal 2 anklicken. Tiefer, ja? Da war eins tiefer, tiefer. Ach, das kann man wegmachen, toll. Und Kanal B einmal anklicken und jetzt einfach mal auf Auto. Thank you. Okay. So I maybe talk a little bit while setting it up, and tomorrow you set it up yourself. Good? Very good. So basically what you can see right now, the red line is the laser distance sensor I'm using here. And you see that it's slightly below 0. So it's actually the laser distance sensor records between or outputs between 0 and 10 volts. And then that refers to 0 to 10 mm. It can't go negative. That's why I did a DC offset. Maybe you can hover with the mouse over the DC offset. So yeah. Lower. Yeah, that. So that's the DC offset of negative 5 volts, just to put it down. So now I can go up and down, 5 volts up, 5 volts down, because I have the negative offset. And the first thing I will try to do is to get it to 0. Let's see whether we can do that. So I have a small wheel here, and with that small wheel, now it's to 0. And now if I push it a little bit, you can already see that it reacts, right? But that was only me. The rest is purely static. Okay, so that is the first thing. Now we have the signal. Now we can see between negative 10 and 10 volts, and maybe you can switch that in the channel to plus minus 5 volts. Can you see all the numbers written there? Yeah, exactly. Just put on that. Yeah. Okay, now we see a little bit more if we. Yeah. So the signal is getting bigger.
Maybe you also have to introduce the setup. What distance are you measuring?
Exactly, and what maybe you can see, I'm not sure if you can see. So what I'm measuring is just the distance between, this is the laser sensor, and this is the piezo ceramic, and the piezo ceramic has a small red dot on top of it, and then you can see this is just the distance. So if I push on top of the laser sensor, the distance gets smaller. So because the distance gets smaller, the peak goes down. But if I now elongate the piezoceramic stack actuator, then the distance gets smaller. So if the actuator becomes longer, the distance gets smaller. So actually we should invert that signal. But since I do not know by heart how to invert it, yeah, you can put invert on. Yep. And now, if the piezo sensor becomes longer, we see a positive signal. Okay, let's see if we keep it like that. I'm not sure yet. So the next thing we do is, now we want to actuate this actuator. So we need to give a voltage on the actuator, right? And this voltage will then transfer to a electric field if you know the distance between two electrodes. Okay, so there's a piezo plate and there are two electrodes, and then there's the next piezo plate, electrode, piezo plate. This will come tomorrow. So the next thing we do a signal where we put first a high field on it, and then we do a negative field on it, and then a high field and a negative. So in the butterfly curve, or in the butterfly diagram, we go from the left to the right, to the left to the right. And then what should happen ideally is that the elongation, which is the y-axis, does exactly what you should see. You should see the butterfly curve in the end. So let's hope that works. It's always a thing with experiments. So could you please turn the function generator, which is the last signal? Yep. Could you turn that on?
Yep.
And could you please turn on channel A?
To manual or to
auto? Auto is fine. So what you now see is, what I prepared is, if you can go back to the function generator, please.
Yep.
What I prepared is, I used a very small frequency of 100 millihertz, not megahertz, millihertz, so 0.1 hertz. So very slowly, we increase the voltage, we decrease the voltage, and we shift between minus 450 and plus 450 millivolts. So that's the amplitude, right? So this is what you can now see, since I connected the signal generator output to the input channel A. You can see on channel A what the function generator outputs. And on the other channel, on channel B, you just see what the laser distance measures. Nothing. That is good.
But this voltage is far too low to drive the piezoceramic stack. It's just a control signal we put into the high voltage amplifier.
Exactly, thank you. And the high voltage amplifier has an amplification of factor 200. So from 0.45, I get volts, I get 90 volts. So now I go between plus 90 volt and minus 90 volts. And now, since the distance of the electrodes is very small, far below 100 micrometers, this is a field above the 2 kilovolts per millimeter, so which was your question. And now, I think we are all good. We turn on the amplifier. Let me just check. Okay, input, output. Okay, and we see what happens. And we hope something will happen. Okay, nothing so far. Could you go to channel B, please? Channel B is, okay. So you can see everything, but the piezoelectric stack actuator only shifts by 40 micrometers maybe. So right now I'm showing 5 millimeters, plus minus 5 millimeters. So what you see is a very small signal. Could you change that to plus minus 100 millivolts, please?
Channel over range.
Okay, 200 maybe? Channel over range, it's bad. 500? Okay, go back to plus minus 5 maybe. Okay, can you put the DC offset to 0? Just press 0 and volts, yeah, whatever. Okay, so what happened here? We definitely need to increase that. Yeah, let's go try. We're still in channel over range, yeah? Okay. Now I have to check what happened. Okay, let me get that up to 0 again. Oh, okay, this is 0. Okay. I think I know what happened. Okay, plus minus 5. Okay, please go back to plus minus 200. Okay, and now set the DC offset to minus 5 volts, if that's possible. Minus 5 volts. Okay.
You can also only offset, I think.
Did it do that?
No.
No, it didn't. Okay, that's the whole point. That's the whole point. It didn't do that. Geh mal zu 1 plus minus 1. Okay. The issue is that the offset always changes with okay. Und jetzt mal zu plus minus 500. Und jetzt mal zu plus minus 200. Oh, sorry. Okay, that's still me, and now I don't do anything, and we just wait. Okay, very good. And now what you can see, first of all, is that always when the, thank you, with the point, right?
Yeah.
Okay, so, I think I use my hand. So always when we pass 0, shortly after, like here, before we reach the maximum of the blue curve, the polarization changes. So the elongation becomes maximum, and then it changes. And then again, here we go above 0. Here we go above 0, and shortly after above 0, the elongation abruptly changes. So this is when the field strength, so when we reach coercive field strength and when it shifts around. And now we see both over time, and if we want to see the butterfly, then let me check if we can see the, if we can see the butterfly now first of all. Kriege ich den noch ein bisschen höher? Ah, okay. Let's check. What's the, wie hoch kriege ich den? Ah, that's wrong, yeah. Okay, that's better. Okay, and now we go to the display where we can see x over y. Den finde ich immer nicht. Scope, Trigger, Wave.
Display is here.
No. Instruments, hardware, rulers, nodes, more. There. Okay, this is good. And if we now see something like persist, is there something like persist? DSQ, no. Name, no. No. Okay, this is already quite good. We can try to get it like this. Okay, now we're going somewhere. Okay, can you recognize, even though the noise is quite big,
high.
quite high, you can actually see how the butterfly is forming, right? So yeah, And usually there's a persist option, so you can, so right now after some seconds it vanishes, and you can set it to persist somewhere, and then it will stay. So if anyone sees persist, please tell me. Deep measure, no reference masks, actions, nodes, more, views, more. Actually, it should be here, right? Waveform. 6 of 6 instrument auto setup. Okay, I do not see that right now. It should be here usually. Oh, okay, and then, okay, so, and maybe the other thing I can tell you right now, since I can't find persist right now, the other thing I can tell you right now, so this is basically an oscilloscope, exactly the same as you will downstairs in hardware, only this is much easier to bring in an aircraft. So yeah, we have those for the live showing experiments. It's a very, very good piece. It's also much cheaper than the oscilloscope, and you can do a lot of stuff with that. The software you get for free. And yeah, for example, we could activate now some band pass to get the noise away and so on, so you could get a much clearer signal. But first, I think for today is what you see, the butterfly curve is a good start on how to use that.
I think so. So thank you very much, Hendrik, for showing us the butterfly curve. And I think with that, we end today after lecture 4, and we start tomorrow then with lecture 5. So see you tomorrow.